Welcome to our latest video, which has the title The Effect of Temperature on Rate, the Arrhenius Equation. This video is suitable for A-level students. By the end of this video lesson, you should be able to explain why temperature affects the reaction rate using collision theory, and be able to calculate the effect of temperature on reaction rate using the Arrhenius equation. Now, in our previous lessons, we've looked at the effect of changing the concentration of reactants on reaction rate, and we've looked in detail at the rate equation and the reaction order. Now, we're going to test your understanding of the concepts we've discussed in previous videos with a few practice questions. So read through the first practice question here, pause the video, have a go at it, and then we'll go for the answers. So this first practice question looks at the reaction of hydrogen and iodine to produce hydrogen iodide, and the question tells you that it's first order with respect to the concentration of hydrogen and first order with respect to the concentration of iodine, and it's asking you in part A to write the rate equation. So rate would be equal to K, the rate constant, times the concentration of hydrogen times the concentration of iodine, and they're both raised to the power 1, but we don't need to write the 1 in because they're both first order. Now it's then asking you to work out the units of the rate constant K, so all we have to do is substitute in the units for rate and the units for concentration into this rate equation. So rate is measured in moles per decimeter cubed, seconds to the minus 1, and this will be equal to K times moles per decimeter cubed times moles per decimeter cubed. And that's because moles per decimeter cube is a unit for concentration, and we have two concentration terms. So to get K, we just rearrange this, and it would be moles per decimeter cube seconds to minus 1 over moles per decimeter cubed times moles per decimeter cubed. And we're able here to cancel out the moles per decimeter cube that's on the top and the bottom here. So that leaves us with K equal to seconds to the minus 1 over moles per decimeter cubed, and we need to write this on the same line, so it becomes moles to the minus 1 dm to the 3 seconds to the minus 1, and that's the units for overall second order reactions. So here's a second practice question for you to have a go at. Once again, read through the question, pause the video, have a go at it, and then we'll go for the answers. So this second practice question is all about the oxidation of bromide ions by acidified bromate 5 ions. And it's asking you to work out the order of each reactant here. So I'm looking to change the concentration of Br- and keep the H plus and BrO3 1- the same. So that's why I would look at experiments 1 and 3 here. And I find that when I triple the concentration of bromide ions, the rate triples. Now that's just the same as doubling the concentration and the rate doubling. So that is a first order relationship here. So it's first order with respect to the bromide ion. So to determine the order with respect to the H plus ions, I need to look at experiment 2 and 4. And here I double the concentration of H plus ions, but I keep the bromide ion at 0.10 moles per decimeter cubed and the bromate ion at 0.2 moles per decimeter cubed. So if I double the concentration of H plus ions here, keeping the other reactants the same, we will see that the rate quadruples from 2.4 to 9.6 times 10 to the minus 3 moles per decimeter cubed seconds to minus 1. So as the rate quadruples when I double the concentration of H plus ions, it is a second order relationship. So the order with respect to H plus is second order. Now if we look at the bromate ion, and I look at experiments 1 and 2, I double the concentration of BrO3 1-, and that results in the rate doubling. So therefore, if I double the concentration of bromate ions and the rate doubles, this is a first order relationship, and the reaction is first order with respect to the bromate ions. So there's 1 mark here for each correct order and 1 mark for the reasoning. So there's a total of 6 marks for this question. So part B is asking you to deduce the rate equation. Now you've already worked out the order with respect to each reactant and its first order with respect to the bromide ion concentration. And we've seen that it's second order with respect to the concentration of H plus ions. And we've seen that it's first order with respect to the Br03 1- ions, the bromate ions. So we can write a rate equation. Rate is equal to K, the rate constant, times the concentration of Br- ions times the concentration of H plus ions to the power 2, because it's second order, times the concentration of bromate 5 ions, Br03 1-, and that would be the rate equation for this reaction. Now in this video, we're going to look at the effect of change in the temperature on the reaction rate. And this next practice question looks at this very concept. So read through the question, pause the video, have a go at it, and then we'll go for the answer. So this question is all about the Boltzmann distribution. And the Boltzmann energy distribution curve shows the distribution of molecular energies in a gas. And the energies of a few molecules will be almost zero, but most molecules have an energy around an average value, and only a small minority of values are equal or exceed the activation energy. Now this question asks you what happens at a higher temperature. Now at a higher temperature, the average molecular energy will increase. So when we sketch the curve at a higher temperature, all that happens is that the distribution flattens and the peak moves to the right and it has a lower height. So you've got to remember that the distribution flattens at a higher temperature. And this is because the average molecular energy will increase. And when you sketch the graph, you have to make sure that the peak is to the right of the first peak and is lower. Now, the reason that it's faster at a higher temperature is because a greater fraction of molecules possess the activation energy or greater than the activation energy at a higher temperature. And I'm going to show you this now on the graph. If I said that the activation energy is this amount of energy, which I'm marking here, on the first curve, I'm going to shade in the area under the curve, which would show the fraction of molecules that have this activation energy or greater. Now notice when I've shifted the curve to the new position and I look at the area under that curve, a greater fraction of molecules now have the activation energy or greater. And that's why at a higher temperature the reaction is faster. A greater fraction of molecules will possess the activation energy or greater than the activation energy at this higher temperature. Now, in this lesson, we're going to look at the Arrhenius equation, which looks at the effect of changing the temperature on the reaction rate in a mathematical way. And previously, we've looked at the rate equation, which tells us how changing the concentration of reactants affects the reaction rate. And in the rate equation, we have a rate constant, K. And this rate constant varies with temperature. So if you quote any values for the rate constant, you have to quote them at set temperatures because changing the temperature affects the value of K. So if we have a reaction A plus B going to products and we write a rate equation, rate is equal to K times the concentration of A raised to a power, let's call it M, times the concentration of B raised to a power, let's call it N, and M and N are the reaction orders, and we determine these experimentally. Now the rate equation shows the relationship between the concentration of reactants and the rate of reaction. And if the concentration of one of the reactants increases, the rate of reaction will also increase, because the rate constant K doesn't change when you change the concentration of reactants. It only changes with temperature. So that's why rate increases with changes in concentration, because you're changing the values of the concentration terms in the rate equation. Now if the temperature increases or a catalyst is added, the rate of reaction increases without a change in concentration of the reactants, and so it must be the rate constant K that is changing. Now you have to remember that the rate constant K varies with temperature and is also affected by the addition of a catalyst, and if the temperature is increased, the rate constant K will increase, and if the temperature is decreased, the rate constant K will decrease. And the exact relationship the temperature has with the rate constant, and ultimately this determines the effect of changing the temperature on the rate of reaction, is governed by the Arrhenius equation. So the relationship between the rate constant of a reaction, K, and the temperature can be quantified using the Arrhenius equation. And the Arrhenius equation can be expressed as follows. K, the rate constant, is equal to A e to the minus EA over RT. Now in this equation, EA is the activation energy for the reaction, and when using this equation, the activation energy needs to be in joules per mole. Now T is the temperature, and when using this equation, the temperature must be in Kelvin. Now remember, 0 degrees C is 273 Kelvin. Now R is the molar gas constant, and it has a value of 8.314 joules per mole per Kelvin, and this is given to you in exam questions because it's on the data sheet if you're studying the WJC course. Now A is the frequency factor, and is sometimes referred to as the Arrhenius constant, and it varies from reaction to reaction. And some exam boards will call it the pre-exponential factor because it comes before the e to the minus EA over RT. Now this factor is related to the frequency of collisions between particles, and it varies slightly with temperature, although not too much. So it's often taken as constant across small temperature ranges. A has the same units as the rate constant K. Now E has a value of 2.71828 and is a mathematical number, a bit like pi, and you don't need to worry exactly what it means, although if you have to do calculations with the Arrhenius equation, you may have to find it on your calculator, and you should find an e to the power x button, probably on the same key as the natural log button. And this is what you'll need to use in these calculations. Now it's also useful for you to have an understanding of what this equation represents in terms of collision theory. Now collision theory tells us that reactions happen when particles collide with the right amount of energy, called the activation energy. Now the equation K is equal to AE to the minus EA over RT represents different aspects of collision theory. For example, the e to the minus EA over RT counts as the fraction of molecules present in a gas which have energies equal to or in excess of the activation energy at a particular temperature. And the term A is the frequency factor, sometimes referred to as the Arrhenius constant or the pre-exponential factor, and this is related to the frequency of collisions between particles. Now the Arrhenius equation contains two constants, E and R, and 3 out of the 4 remaining factors, K, A, EA, and T, must be known to calculate the value of the final factor. Now in questions you will face at A level, we can work out the value of A at one temperature from a series of data, and then if we make the assumption it remains constant with small changes of temperature, we can use it to find a new value of the rate constant K at a different temperature. And that's how a lot of these questions you'll come across at A level work. You work out the value of A given data, and then you use this value of A to work out the rate constant K at a completely different temperature. And you're making the assumption that A doesn't change with small rises in temperature. So we're now going to go through a worked example to aid your understanding of what we've learned so far about the Arrhenius equation. Now if you'd like to have a go at this question before I go through the solution, pause the video and have a go at it. Otherwise, fast forward through to the solution. So this question says the reaction between iodine and hydrogen to produce hydrogen iodide has a rate constant of 1.37 times 10 to the minus 4 moles to the minus 1 dm to the 3 seconds to the minus 1 at a temperature of 575 Kelvin. Now the activation energy for the reaction is 157 kilojoules per mole. Calculate the value of the frequency factor given its units and use this to find the rate constant at a new temperature of 600 Kelvin. So step 1 here is to find the value of A. Now A is the frequency factor, and we're going to make the assumption here that going from 575 Kelvin to 600 Kelvin would not change the value of A. So to work out the value of A, we're going to rearrange the Arrhenius equation. And this is K is equal to AE to the minus EA over RT. Now if we substitute the values that are given to us in the equation, K is equal to 1.37 times 10 to the minus 4. The activation energy EA is 157 kilojoules per mole. Now that has to be put into joules. So you can see I've got 1.37 times 10 to the minus 4 is equal to AE to the minus 157,000, because it has to be joules, over 8.314, the value of R, times 575, which is our temperature in Kelvin. So 1.37 times 10 to the minus 4 is equal to AE to the minus 157,000 over 8.314 times 575. Now to simplify this sum and avoid calculator errors, I'm going to work out what 157,000 over 8.314 times 575 is, and it comes out to be 32.84. Now remember, it's e to the minus this, so it's e to the minus 32.84. So I'm going to rewrite my equation. It's going to be 1.37 times 10 to the minus 4 divided by e to the minus 32.84, which is equal to A, because I've just rearranged this equation. Now, when you put this into the calculator, you should get a value of A that comes out to be 2.51 times 10 to the 10. Now, the value of A is this, and the units will be the same as the units of K. So K has units of moles to the minus 1, dm to the 3 seconds to the minus 1. So therefore my answer for A, and this is the first step that I have to work out, is 2.51 times 10 to the 10 moles to the minus 1, dm to the 3 seconds to the minus 1. Now once you work out the value of A, you make the assumption that this doesn't change with small increases in temperature. So step 2 is to find the value of the rate constant at a new temperature of 600 Kelvin. And to do this, I'm going to need my value of A, which I've already calculated. So once again, I use my Arrhenius equation. So this will be K is equal to AE to the minus EA over RT. So K is equal to 2.51 times 10 to the 10, which is the value of A, times E to the minus EA over RT, which is 157,000 over 8.314 times my new temperature of 600 Kelvin. And if I work this out now, because I'm trying to simplify this sum, 157,000 over 8.314 times 600 comes to be equal to 31.47. So this can be simplified as e to the minus 31.47. So my value of K is equal to 2.51 times 10 to the 10 times e to the minus 31.47, which is equal to 5.38 times 10 to the minus 4. And my units will be the same as my units of A, and the units of the rate constant at 575, and that will be moles to the minus 1, dm to the 3, seconds to the minus 1. So now let's test your understanding of this with some practice questions. Here's the first practice question. Read for the question, pause the video, have a go at it, and then we'll go for the answer. So this question says to calculate the value of the rate constant K when T is equal to 300 Kelvin, A is equal to 0.3, and the activation energy EA is equal to 50 kilojoules per mole. So if we use our Arrhenius equation, K is equal to AE to the minus EA over RT, where T temperature is equal to 300 Kelvin, A is equal to 0.3, and the activation energy is equal to 50 kilojoules per mole, which is 50,000 joules per mole. And we have to use joules per mole in this equation. So K is equal to 0.3 times e to the minus 50,000 over 8.314 times the temperature 300. And remember, R is our gas constant, which is 8.314. So if I simplify this by working out what 50,000 over 8.314 times 300 is, this comes out to be 20.0465. So I've now simplified the e to the minus 50,000 over 8.314 times 300 as simply e to the minus 20.0465. So I've put this value into the equation. We have K is equal to 0.3 times e to the minus 20.0465, and this will be equal to 5.9025 times 10 to the minus 10. And you don't have to put units here because the question says no units are required for K in this question. So here's a second practice question. Once again, read through the question, pause the video, have a go at it, and then we'll go for the answer. So this question is asking you to calculate the rate constant using the Arrhenius equation, given the following values for a reaction. A is equal to 2.22 times 10 to the 11, and EA is equal to 111 kilojoules per mole, and the temperature is 444 degrees C. So K is equal to AE to the minus EA over RT. We know the value of A. We know the activation energy is 111 kilojoules per mole. And the temperature is given in degrees C, and we have to convert this to Kelvin. So K is equal to 2.22 times 10 to the 11 times E to the minus 111,000, because 111 kilojoules, and we need to convert it to joules per mole, divided by 8.314, the gas constant, times the temperature. Now the temperature has to be put into Kelvin. Now 0 degrees C is 273, so 444 degrees C is 444 plus 273, which comes out to be 717 Kelvin. So I'm putting that into my equation. Now once again, I like to simplify this by working out what 111,000 divided by 8.314 times 717 is. And this comes out to be 18.62. So I've simplified e to the minus 111,000 divided by 8.314 times 717 as e to the minus 18.62. So k is equal to 2.22 times 10 to the 11 times e to the minus 18.62. And if you put these values into the calculator, you will have a value for k equal to 1,818.82. And we have to include units here, so the units for k are the same as the units for A, so therefore the units are moles to the minus 1, dm to the 3, seconds to the minus 1. And you have to remember that the units of A are always the same as the units of k. So here's our final practice question. Read through the question, pause the video, have a go at it, and then we'll go for the answer. Now in this question you're given a table and it shows how the rate constant varies at different temperatures, and it's asking you to use the Arrhenius equation to calculate the pre-exponential factor A at 290 Kelvin if the activation energy was 55.5 kilojoules per mole. So K is equal to AE to the minus EA over RT. Now the value of K we use is the one at 290 Kelvin. Now this is 0.0030, and this is going to be equal to A times E to the minus EA over RT. And EA, the activation energy, is going to be 55,500. And the activation energy is 55,500 because we have to put it into joules. And we divide that by 8.314 times the temperature, 290 Kelvin. And if we simplify this, we get a value for this as 23.0189. And therefore, it would be 0.0030 equal to A times E to the minus 23.0189. And if we rearrange this, we get 0.0030 divided by E to the minus 23.0189 equal to A. Now this gives you a value of A equal to 2.979 times 10 to the 7, and the units are the same as K, so it will be moles to the minus 1, dm to the 3, seconds to the minus 1. So that concludes this video lesson. So after watching this video, you should now be able to explain why temperature affects the reaction rate using collision theory, and you should also be able to calculate the effect of temperature on reaction rate using the Arrhenius equation. So that concludes this video lesson. So please check out our YouTube channel, Dr. O Chemistry, which has lots of GCSE, AS and A-level videos, and our Twitter site @RadaChemistry.